Hello and welcome to ENGR 330 Fluid Mechanics. Today we'll look at recitation or problem solving based on chapter 4. And remember, for you to accomplish a lot of problems in this chapter, you have to be really good with differentiation and integration. Let's look at a problem. You're given the components of a velocity field are given by u equals x plus y, v equals x cubed plus x times y cubed plus 16, and w equals 0. We're asked to determine the location of any stagnation points, that is when the velocity is 0 in the flow field. So we know that we can compute the magnitude of the velocity, and you see that you're given three components. So the magnitude of the velocity would be square root of sum of squares of magnitudes in the u component, v component, and the w component, right? Or if you want to write it in a vectorial form, you can write this way. Okay, so let's try to put in what we are given and see what we end up here. So we're given u, which is x plus y whole square plus square of v, and I'm not going to put w squared because that's 0. So what this tells us is when the stagnation point occurs, v will be equal to 0. So we solve x plus y whole square plus x cubed plus 16 square equals 0. Or in other words, we can say that the component u, which is, if I write just the component here, x plus y, should be equal to 0, and v, which is x y cubed plus 16, should also be equal to 0. So you see that we have two equations and two unknowns, which is x and y. So we can solve this set of equations, and if you solve it, or let me do this here because there is an interesting thing which would happen here. I can write from here x equals negative y, and if I substitute that in here, I get y power 4 equals 16. So you see that this equation you'll end up with 4 roots, but only 2 of them would be real, 2 of them will be complex. So that would mean that if I consider only the real part, y is plus or minus 2, right? So similarly, x will be, since x is negative y, x will be plus or minus 2. So therefore, for v equals to 0, the coordinates or x comma y can be 2 comma negative 2 or negative 2 comma 2. Okay, now let's look at another problem. So the velocity of the water in the pipe shown in the figure here is given by v1 equals 0.5 times t meters per second and v2 equals 1 t meter per second, where you're given that t is in seconds. You're asked to determine the local acceleration at points 1 and 2, and you're asked to determine or tell us if the average convective acceleration between these 2 points is negative, 0, or positive, and you're asked to explain. So the local acceleration at any point would be dv over dt, and if I want to compute this at point 1, this is over dt of 0.5 t, or just 0.5, and the units would be meter per second square. Similarly, at point 2, I can determine that it would be 1 meter per second square. So this is a situation where this is an example of a nozzle. So you see that the velocity is increasing as it goes through this contraction. It's going from a higher area to a lower area. So obviously you can say that V2, even from the data for any t, V2 is greater than V1. And also, if I consider this as my x direction, dv over dx will always be greater than 0. See? And also for t greater than 0, we know that v is always going to be a positive value. So the, the convective acceleration, which is given by v dv dx, since we determined v is always greater than 0, dv dx will be greater than 0, is positive for the current situation. Okay, let's look at another problem. So as a valve is opened, water flows through this diffuser. So this is another example. We have looked at a nozzle before. Now this is a diffuser where the velocity reduces as it flows through here because of larger area compared to this smaller area for this same flow. So, and it's increasing flow rate, so that velocity along the center line is given by this. And you're given that u0, c and l are constants. You're asked to determine the acceleration as a function of x and time. And if v0 is 10 feet per second and l equals 5 feet, what value of c other than c equal to 0, that means not a trivial solution, is needed to make the acceleration 0 for any x at t equals 1 second. And you're asked to explain how the acceleration can be 0 if the flow rate is increasing with time. Okay, so you're given the velocity. Let me write that, u times I, which is v naught 1 minus e power negative ct times 1 minus x over L times the unit vector along the x direction. Okay, so that's your velocity vector. You see that it is a function of x and also time. So acceleration is dou v dou t plus the local acceleration times plus the convective acceleration terms. Okay, and you see that in this problem we have only one component u. The v and w components are zeros. Okay, so we can simplify this as dou u dou t plus u dou x, and we should carry the unit vector since we are talking about a vector quantity here. Okay, and we already know what is u. If you compare it here, u is nothing but v naught times 1 minus e power negative ct times 1 minus x over L. Okay, so now you have to determine these two terms here. First thing is you have to take a partial derivative of u with respect to t, and also partial derivative of u with respect to x. Okay, so I'll let you do that, and you should end up with, if I'm talking about the x direction acceleration component, okay, you should get it as V naught times 1 minus x over L times c e power minus ct minus V naught over L times 1 minus e power negative ct square, and I should have an I because I'm talking about a vector on the left hand side. Or if you want to just write the magnitude of the component, you can take out this vector and you can get rid of the I unit vector here. Then it'll still be okay. So we are asked to determine the value of c when this acceleration is 0. And so this is what is the situation we have, and we're asked to determine c for any x and at t equals 1 second, and we are given that v naught is 10 feet per second and L is 5 feet. Okay, so we know that if you look at this, all these numbers are finite, so this cannot be equal to 0. So only term this, since it's a product of three quantities, if one of these have to be equal to 0. This cannot be equal to 0, so this has to be equal to 0. Okay, so we have c e power minus ct minus v naught over L times 1 minus e power negative ct whole square equals 0. So if you substitute what we are given here for t, v naught and L, we end up with c e power minus c minus 2 times 1 minus e power negative c square equals 0. Okay, so we have to find the solution of this equation to determine c. So you see that c, if you substitute c equal to 0, it is a trivial solution. You will satisfy the equation, but that's not you're asked to find. And since it's a quadratic equation, you'll end up with another root. So the easier way to do this problem, since you cannot easily solve it by hand, is you can use any calculator or online tool. For example, here I used Wolfram Alpha, which is an online free calculator where you can say solve and your equation, okay, and it will show up the way you have written here, so it looks right. And then you see that it has two solutions. One is 0, which is okay, but we don't want that as a part of the solution. We wanted a non-zero value. So the other solution is c is 0.49. Okay, so that means c is 0.49, but make sure you write the units. Okay, this would be 1 over second. Okay, and the reason being, if you look at this term here, and if you want to compare it to make sure it is dimensionally homogeneous, you can determine then that c would be 1 over second, because this is non-dimensional. This is meter per second, so we have a meter per second, so that satisfies. So this should also be a non-dimensional quantity. So e power c times t, t is second, so c has to be 1 over second. So that's the reason why I end up with c equals 0.49 times second to the negative 1. So we have to answer the second part of the question. So with these conditions, you see that the local acceleration is greater than 0. Okay. And when the acceleration is 0, This term is balanced by the convective deceleration. This term u times dou u dou x is less than 0. Okay? And you can find that basically from what you did earlier. If you look at this equation here for the acceleration, you see that if you take these guys inside, get rid of the parentheses, this is positive, this is a positive quantity, and these guys are always positive. Okay, so that's the reason dou u dou t is greater than 0. Whereas if you look at this term, if you take these guys inside, there is a negative sign here. V naught times V naught is always a positive square of any quantity. L is positive, and 1 minus e power negative c raised to the 2 is always positive. That means you'll end up with a negative quantity. So that is always 0. So that means the flow rate increases with time, and at the same time the fluid can flow to an area of lower velocity. Okay, let's look at another problem. A gas flows along the x-axis with a speed of v equals 5x meter per second and a pressure of P, which is 10 x square Newton per meter square, where x is in meters. We're asked to determine the time rate change of pressure at the fixed location x equals 1, and also determine the time rate of change of pressure for a fluid particle flowing past x equals 1. And in part C, we're asked to explain without using any equations why the answers to part A and part B are different. Okay? So let's look at part A. So you're given P equals 10 x square. Okay, you see that P is only a function of x here. So if I want to determine the time rate change of pressure, this will be 0 for any value of x. Okay, and if you want to determine the time rate change of pressure for a fluid particle flowing past x equals 1, we're talking here about the material derivative, okay, which I can write as dou p dou t plus u dou p dou x v dou p dou y plus w dou p dou z. Okay, this we determine to be 0. We don't have the v and w components. Okay, nor the pressure varies with y or z. Okay, to do that, we get p over u times dou p dou x. Okay, so this is a simple partial differentiation. You know what u is, okay, which is 5x meter per second, and you take the partial here, this would be 20x, so that would mean you get 100 x squared. The units would be Newton per meter square second. Okay, and you're asked to determine this at x equal to 1, so let's plug that. So dp over dt at x equals 1 would be 100 Newton per meter square second. Okay, and in part C we are asked to explain the situation here. This is a steady flow, right, which we determined. Both v and p are not a function of t. However, the pressure of a particle changes with time if you look at the material derivative, because the particle actually flows into a higher pressure region because x increases as we go along in the positive direction. Now let's look at another problem. A layer of oil flows down a vertical plate as shown in this figure, and you're given the velocity profile, and this is your y direction, this is your x direction, and your v naught and h are constants here. First, you're asked to show that the fluid sticks to the plate and that the shear stress at the edge of the layer at x equals h is 0. And also you're asked to determine the flow rate across the surface AB, and you're asked to assume the width of the plate, that means if you're talking about the depth here, into the paper is B. Okay? So if you look at part A, this is what we know as the no slip condition. So fluid sticks to the plate in the sense at x equals 0, your velocity should be 0. So we have v equals v naught over h square times 2hx minus x square, and I'm dropping the j here, I'm talking about only the magnitude here. So let's evaluate what is v at x equal to 0. So if we substitute, this is 0, this is 0, so 0 times any non-zero number, any number is 0. So the fluid sticks to the surface because the no slip condition, which is v at x equal to 0, is 0. Now we are asked to show that the shear stress at the edge of this layer is 0. So we also learned this in chapter 1, where the shear stress is mu du, or in this case dv, and the x here is like your y in chapter 1, so it doesn't have to be always y, so remember what you're talking about in terms of the coordinate system. Okay, so let's evaluate this du dx. So v naught over h square is a constant, so I have 2h minus 2x. Okay, so tau at x equals h, you see that if this is 0, so 0 times anything is 0, so this is 0. So we have proved here that the fluid sticks to the surface here of the plate, and also the shear stress at this surface, which you can also call as a free surface, is 0. Okay. Now let's determine the flow rate which across this surface AB. So flow rate in general, you can write it as V times A, right? Whereas in this case, since we cannot really compute an area here, but we can take a small element of the area, so I can integrate, write this as V times dA, okay, where I'm integrating all the small areas, and I want to integrate from x going to 0 to x going to h, and I can write the area dA as the width of the plate times some small length in the x direction. Okay? So I can evaluate this. So I know V, which is V naught over h square times 2hx minus x square times b times dx. This is a constant, this is a constant, this is a constant. So V naught b h square. So if I do the integration here, okay, So what I end up here for flow rate across AB is 2 over 3 V naught H times B. Now let's look at another problem. The wind blows across a field, which is shown here, with an approximate velocity profile. Okay. See that it is 0 at the wall or at the grass here, gradually linearly increases, and it's about 15 feet per second all the way across from 10 to 20 feet. Okay. And with the parameter b equal to the velocity in equation 4.16, okay, and I'll quickly write that here. Equation 4.16 from your book in chapter 4 is b out equals cs out rho b v dot n dA. This is equation 4.16. And you're asked to take the parameter b as the velocity, and which will then help you to determine the momentum flow rate, which will be this quantity then, across this vertical surface AB. And you're asked to assume that the depth into the paper is unity. Okay, so let me rewrite this guy here, since I know that the b here is the velocity. Okay, so if I want to write this as a vector quantity across AB, so the cross section here is AB, okay, rho times B, okay, and V here, V, which we have V dot N, the normal, okay. Okay, so density is a constant. We can assume that it is incompressible. It's a safe bet here. So rho, and then if I want to take out the unit vectors here in these guys, I get I here, and then I get 0 to 20 v square dy. And v dot n, the way you determine is n is always a normal vector going out of the surface, and you see that both of them are in the same direction, so this becomes a positive quantity, so v square dy. At this point you might want to just pick something here 15 feet and do it, but that would be wrong to integrate this quantity here, because you see that the velocity is not really constant across the 20 feet here. So you have to consider this integration into two parts. First, integrate from 0 to 10, okay, and then from 10 to 20 it is again 15 feet per second. Okay, so it's very easy to come up with this guy here. You know that the velocity here is 0, the velocity is 10. It's a simple linear equation passing through the origin of the form y equals mx. So I'll let you get that. So you get v equals 15 over 10 y, and that is feet per second, and this is in the region where y is equal to 0 or equal to 10, or between 0 and 10. And the way I determined this is at y equal to 0, and I'll call this as y. Okay, at y equal to 0, v is 0, sticks to the surface, and at y equals 10, you see that v is 15 feet per second. Okay, so that satisfies that part of the flow profile, whereas v will be 15 feet per second for y, for any y greater than or equal to 10 feet, as you can see from the picture. Okay, So I can do the integration now. Rho I going from 0 to 10, 15 over 10 y square, should put a square here too, dy plus 10 to 20, 15 square dy. Okay, and I'm sure you can compute this integration and do the definite integration where you apply the limits. Okay, so you should end up with, to do this math correctly, should end up with 7.14 I pounds. Okay. Alright, so this concludes the session for recitation or problem solving in chapter 4. Hopefully this should help you to put in some quality effort into your homework and help you understand the concepts better. Looking forward to seeing you again. Have a great semester.